Hello, everybody. Welcome to the Intelligent System session. We have six authors today, and the first one is Arjun Srinivasan, and the title is Interweaving Model Interaction with Flexible Unit Visualization for Data Exploration. So I will ask the first author to start talking.
Hello everyone, I'm Arjun Srinivasan. I'm a PhD student at Georgia Tech, and today I'll be talking about interweaving multimodal interaction with flexible unit visualizations for data exploration. And this work done in collaboration with Bongshin Lee from Microsoft Research and John Stasko from Georgia Tech. So to set up the context a bit, since we're talking about multimodal interaction, I thought I'll start by playing a short video snippet from Richard Bolt's famous Put That There demonstration.
Put that there. Move that below that. Move that west of the diamond. Create a large green circle there. Oh, shit.
Now, even with the limited technology at the time, we can see how this video illustrates the vision of combining different modalities like speech and gestures, and how interactions could be used, or how such multimodal interactions could be used in the context of a graphics interface. And while we've seen a growing suite of natural user interfaces for visualization, especially over the past decade or so, we haven't quite achieved this sort of vision suggested in Bolt's demo. So, a goal with this discovery and exploration focused research was to do just that. Specifically, we wanted to see how far we can push the notion of multimodal interaction with visualizations and give users the freedom to interact with their data however they want without confining them to chart types and operations supported in conventional visualization tools. And with this high level goal in mind, we looked at how we can use pen, touch, and speech as input modalities, but specifically to let people interact with unit visualizations. And before I get into too much detail, I'll first show a short video illustrating DataBreeze, which is a system that we built to operationalize this idea of interweaving multimodal interaction with flexible unit visualizations. To give some more context for the video, here I'll be demonstrating how you can use DataBreeze to explore a dataset of US colleges with the goal of shortlisting a set of schools that you're interested in. And as a unit visualization, each point that you're going to see on the screen maps to one data row or college in this case. And by default, I've also colored the points by the region attribute to improve visibility. And a quick heads up, the video is going to run for about a minute and a half, but it'll help contextualize some of the discussions that follow. Region. Move the schools in the far west to the top left corner. Bring the New England schools here. Order by admission rate. Repeat. Can you remove schools that need a SAT average of less than 1200? Now color these points by the school type. Could you remove schools that have an average cost of over 25,000? Can you show the school names for all the green points? Now, I hope that in addition to making you all aware of my subpar drawing and acting skills, the video also gave you a sense for how the tool works and how it lets you customize the view to impart your subjective preferences. Now, in terms of system design, because the goal here was to enable this more free-form style of data exploration, we followed an iterative design process to first identify the set of operations and interactions that we needed to support, and then compiled them into a set of design goals. And you can get more details about these in the paper, but I'll highlight just a few of these now to give you some sense for the intricacies involved in developing a system like DataBreeze. So one of the key challenges we had here was that we wanted to let users leverage standard representations like scatter plots and unit column charts, but then also have the ability to flexibly adjust the view so it best maps to their mental model of the data space. And doing this needed to support this notion of global and local views. So let's watch an example to understand this better. In this first case, I swipe and speak an attribute name to create a unit column chart, which is a global view because the positions of all the points on the canvas are now bound to the region attribute on the x-axis. And after creating this global view, I then pull out a set of schools and reposition them based on my external knowledge of where New England is. But when I do this, the canvas gets into this hybrid mode where most of the points are still positioned on the x-axis by the region attribute, but now there's this one set of schools that are manually placed. So to indicate that these points are no longer bound to the global x-axis, we add some additional affordances like a pin icon. And with the soft separation between global and local views, I can now freely interact with a subset of the data points that I'm interested in, while still preserving the global view for context and future exploration. Another really subtle but crucial challenge we had was thinking about when should the system start listening for speech commands. So let's see a couple of these examples to understand this better.
Can you remove schools that need a SAT average of less than 1200?
So in this first example on the left, I explicitly double tap on the canvas almost as if I was knocking on a door to trigger voice recording and then speak my command. But such explicit triggering can be interruptive, especially during multimodal interactions, because people would have to perform gestures, then trigger the voice input, and then actually speak the command. But on the other hand, we can't have a system that's always listening because it gets difficult to disambiguate when someone's thinking aloud versus issuing a command, and also there's some privacy concerns associated with that. So to tackle this, we built in some smarts into the system to implicitly start listening when specific gestures are being performed. So something like this.
Region.
So in the second case, I'm swiping and speaking at the same time. So it's not always listening, but it still lets you do things like swiping and speaking in one full motion by automatically triggering voice input once you swipe. Finally, with so many possible commands, an inherent problem, of course, with speech is that of discoverability. And DataBreeze tackles this by leveraging multimodal interactions with the more familiar modalities of pen and touch. So as shown in these two examples on the screen, the system presents contextual command suggestions both preemptively when you're interacting with menus in the system as well as post hoc once you've performed an action with pen or touch. Now with these examples on discoverability and even the video that I showed earlier, you can see that the whole idea of multimodal interactions and using the complementary nature of modalities is really what forms the core of DataBreeze's interaction experience. And in terms of what actually enables this, here's what the system architecture looks like. You can find specific implementation details in the paper, but I'll walk through one example to give you a quick overview of how things work. So say we take the example of pointing on the canvas and saying something like, bring the New England schools here. So to process this interaction, the system needs to infer three things. The first one is the action or the operation. The second is the parameters corresponding to that operation. So in this case, the XY positions, the points have to be moved to. And finally, the target or the subset of the data items that the operation has to be applied to. So let's walk through how the system processes these bits of information from the current interaction. So once it receives both the touch and speech input, which is in this case pointing and speaking a command, it splits the input streams and sends them into two different processing modules. These modules then infer that touch is being used to point to a specific location and that the spoken query references a value under the region attribute and has the keyword here in it. And by fusing the pointing gesture with the keyword here, the system is then able to figure out that move is the intended operation and also infers its parameters in the form of the XY positions. And then passing all of this information back to the UI, the system then updates the positions of the points on the canvas. So once we had the system built, we ran a preliminary user study to see how people actually use DataBreeze. And we saw a variety of ways in which participants explored the data through the different types of views that were afforded by the tool. And these range from global views like simple scatter plots to more hybrid views that combine data-bound encodings with participants' subjective preferences. Participants also commented positively on the high level of expressivity that DataBreeze offered, saying things like working with DataBreeze was like using an artboard, or that it mimicked physical interaction like you were working with objects on a table. Speaking to the fluidity of the interactions themselves, even some participants who were initially hesitant about using multimodal input said that they eventually got used to it and actually did so pretty soon and found it to be an effective style of interaction. All right, so that was an overview of DataBreeze. And just to summarize, the main point I want all of you to take away from this talk is that while we've historically seen interaction and representation as these two related but still separate entities within visualization research, especially as we consider post-WIMP and multimodal input techniques, there's a lot of value in exploring how we can interweave these two concepts. And as one specific example of this idea of interweaving interaction representations, in this work, we looked at how we can augment multimodal interaction with flexible unit visualizations, showcasing how this combination can facilitate a novel and free-form data exploration experience. And with that being said, I thank you all for tuning in, and you can find the papers, slides, and more videos of the system on the URL listed in the top right corner of the screen. Thank you.
Okay, thank you, Arjun. Very interesting talk. We have a few questions from the people that are listening. So the first one is actually is an exclamation about about the disappointing activity of the system in a VIS talk. And then, so the question is, how far back does the system infer action to repeat? It is related to the mechanism of the user to refine and tweak these interfaces when it inevitably gets it wrong, a la programming by demonstration. And more in general, this approach seems to run headfirst into a lot of challenges for programming by demonstration.
Right. So I see the point there, and it's important to realize that the core idea driving this system was this combination of direct manipulation and natural language, where direct manipulation is afforded by pen and touch, and natural language is speech. So a lot of the motivation is similar in the first step, which is users can use direct manipulation to kind of perform whatever actions they're interested in. The place where this differs, and which is why it doesn't kind of have the exact problems that PVD has, is that there's no generalization step here. You perform an action and the system kind of stops at that state. And that said, in terms of kind of preserving context, it only looks at the previous action and then continues that as far as it makes sense. So for instance, in that case, when I said order these points and then kept selecting and repeating, every time that I do that, the system also gives this option saying, okay, I inferred this based on your previous action. If you don't feel this is the right one, kindly, you can undo it at that moment instead. So you're not getting into the same problems of generalization and kind of preserving the wrong context again and again.
Okay, thanks. So we are running out of time. So I want just to ask another quick question is about the possible operation about the user. So how do the user learn what is possible with this tool?
Mhm. In part, that was covered by the way we designed the system. We were very iterative in the process. So we kind of gave an open-ended system and we saw what kind of operations people performed and then came up with the set that we have. In addition to that, how the operations are performed is again covered a little bit by the discoverability features that we have. So we give suggestions of what actions can be done both before an action is performed as well as after you perform actions with certain modalities. So a combination of that we found was decent enough for people to get familiarized with the tool in about 5 to 10 minutes of a practice session. And then, of course, like any other tool, they kind of get better with it over time. That was our observation with the studies.
Okay, thanks. I'm sorry not to ask other question, but it's time to switch to the other speaker. Thank
Sure.
you again.
Yeah.
So now it's time for uh, Shayan Monadjemi, competing models, inferring exploration patterns and information relevance via Bayesian model selection.
Thank you for attending my presentation. My name is Shayan Monadjemi, and today I'll be presenting our paper, Competing Models, Inferring Exploration Patterns and Information Relevance via Bayesian Model Selection. In today's presentation, I'll start with some introductory and background information, then I'll introduce the Competing Models framework, then I'll present some of our experimental results, and finally, I'll discuss the future research directions. One of the primary research goals in visual analytics is to build a collaboration between interactive visualizations and humans, where humans are trying to accomplish a task in vague terms. Now, studies suggest that with an interactive visualization alone, there are still human-related challenges that hinder data exploration. So, for example, analysts often search through a large amount of information where the irrelevant portions of the data can be distracting and exceed human cognition. This could cause information overload. We could build more intelligent visualization systems that understand what the user is looking for and automatically filter to mitigate this information overload. Another example is that everyday users may interact with only a biased subset of data, which impedes decision making. An approach to solve this problem is to build intelligent visualization systems that detect those biases and in some form or fashion mitigate them. So the question we seek to answer in this work is how can we infer user exploration patterns by simply observing their interactions with the visualization? And how can we turn those into models that inform the visualization system about the user? In this work, we consider multidimensional datasets, where there is a two-dimensional visualization associated with them, and each point in the dataset corresponds to one point on the visualization. A user may interact with such point-based visualization through different patterns in terms of which attributes drive interactions. In the competing models framework, we enumerate each of these possibilities. For example, a user may only interact based on attribute 1 of the dataset, or a user may interact based on all 3 attributes in the dataset. We name each of these possibilities a model, so we have model 1 through model 8 in this example. The critical part of this competing models framework is using Bayes' rule to infer which models are plausible given user interactions. The last piece of this Bayes equation here is a prior, meaning what is our belief over each model explaining user interactions before any interactions are observed. So an example for this distribution could be just a uniform, meaning we are equally uncertain about each of these models being the correct model. The first piece of this equation is the posterior, which explains how likely a model is to be true given the interactions we've observed from the user. So just to be clear, in this work, when we say interactions, we are referring to the set of points a user has interacted with. So they could be interacting with these points by hovering, or they could be interacting with these points by clicking. That's something we'll specify when it gets to the experiment section. The likelihood function, which is the middle piece of this equation, is a measure of how well observed interactions are explained by a model. Our framework is flexible in terms of which likelihood practitioners choose. In other words, practitioners may choose likelihood functions based on their modeling objective or the underlying dataset. On this slide, I will visually explain our model definition for information relevance. This model definition is our likelihood function, which tells us how well a set of observed interactions, again the data points the user has interacted with, are explained by a given model. We model information relevance with a multivariate Gaussian representing the continuous attributes and a combination of categorical distributions for each discrete attribute. For example, consider a dataset with 2 continuous attributes and 1 discrete attribute. As shown in the figure, attribute 1 and attribute 2 are continuous ones, and attribute 3 is a discrete one. Before any interactions are observed, our belief over these attributes is uninformative, meaning it does not contain any information about what a user is interacting with. This is shown in the figure as a uniform categorical distribution over attribute 3 and a multivariate Gaussian centered in the middle of the data space for attribute 1 and attribute 2. As users start interacting with this data, we update these models iteratively to reflect past interactions. So for example, from time step 2 to time step 3, we update our multivariate Gaussian to contain the 3 interacted points better, and we update our categorical distribution to reflect the categories with which the user has interacted. In order to turn these distributions into probability values for each data point, we first normalize to get the probability mass function, and then we multiply the probabilities for each attribute. In the rest of this presentation, we use these competing models in order to accomplish 3 things. First, we show that we can predict future interactions using competing models. Second, we show that we can detect exploration bias with these competing models. And finally, we show that the parameters of these models summarize interactions. We validate our technique using 3 published user study datasets with different characteristics. The first experiment was conducted by Ottley et al., where the users were directed to perform specific tasks with a map of crimes in St. Louis. The position of dots on this visualization indicate the location of the crime, and the colors indicate the type of the crime. The 6 tasks performed by the users were categorized into 3 groups: geo-based, which are the tasks based on a certain location; type-based, which are the tasks based on a certain type of crime; and mixed tasks, which involve both location and crime. First, let's look at one of the single sessions of a user interacting with the visualization in order to answer one of the 6 questions. So just to introduce my visualizations here. At the top, I have the full crime data set, and those are the locations. The dots, the position of the dots indicate the location of the crimes, and the colors indicate the type. In the bottom, I have the distribution of the types of the crime. So as you can see, the theft-related crimes are the majority of the ones on the map. So in terms of models, at first, our models are not informative. In other words, in terms of location, the models do not know where the user is going to be looking, and the type models are uniform across all types of crimes. As user interactions arrive, so after 5 interactions, the models have updated to reflect what the user has interacted with. So we can see that the location is narrowing down to the area where the clicks have happened, and the types of the crime are updated to reflect that all the clicks were related to assault crimes. And so on, after 10 clicks and 20 clicks, we see that that area gets narrower and narrower into what the user has been clicking. And interestingly, this session corresponds to the question that asked the user to explore non-aggravated assaults within a region and count how many of them there exists. Furthermore, we evaluated our technique against a couple of baselines. First, we evaluated our model's ability to predict future interactions against the hidden Markov model approach by Ottley et al. As shown in the figures, we have on the y-axis average accuracy of predicting feature clicks, and on the x-axis we have the size of the prediction set. So for example, when k is equal to 10, it means that we pick the top k promising points, and the next interaction being a member of that top k interesting points is a success, is considered a success. So as shown in the three figures for geo-based, mixed, and type-based tasks, our technique outperforms the Ottley et al. Approach, especially for lower values of k's. Second, we validate our model's ability to detect bias and compare it against the metrics offered by Wall et al. As shown in the figures, the x-axis is the number of observed clicks, whereas the y-axis is the average probability of ground truth bias, averaged across all sessions for a given type of task. Our technique outperforms the metrics offered by Wall et al. For geo-based and mixed tasks, while the Wall et al. Technique outperforms us for type-based tasks. After further investigations, we realized that this difference in the type-based task is due to the Wall et al. Technique considering the underlying data distribution when detecting biases, whereas ours does not. The second user study dataset we consider is the Feng et al. Experiment, where the users are asked to interact freely with a dot visualization of S&P 500 companies. As they hover on each of these dots, they get a summary of the ratio of women on the boards of directors, or the age, or the tenure of each of them. The users also had a search box available, and they could search for specific companies if they chose to. In this example, we do not know the ground truth of what biases should exist. So for example, the users were not specifically asked to explore this dataset based on the market capitalization or based on the ratio of women on board. Therefore, we do not evaluate this dataset against the Wall et al. Technique. However, we do evaluate it against the Ottley et al. Approach for next interaction prediction. While the average accuracy values are low, our technique outperforms the Ottley et al. Approach in higher values of k as shown in the figure. Finally, we apply our technique to a user study dataset collected by Kern et al. In this experiment, participants were directed to freely interact with a map visualization of St. Louis crimes and report insights as they find them. So, in one example session, the users started clicking on the points around a certain region, and after 10 clicks, they reported an insight saying 2 cars were stolen in the same week from the 3900 block of Miami Street. In this paper, we offered a new perspective towards user modeling. While our modeling objective was centered around which subset of attributes drive exploration, the computing models framework can be applied to so much more. We know task taxonomies are different, visualizations and datasets are different, and human characteristics are different. The key to future work for this paper is to apply computing models using different likelihood functions and modeling objectives, and get closer to informing the machine about their human counterparts by passively observing interactions. At this time, I'll be happy to answer any questions. Thank you for attending my presentation.
Okay. Thank you, Shayan. So there are a couple of questions for you. The first one is, how are the models synthesized from data? The paper and talk described the case with location. How does it generalize to other datasets visualization with multiple different kinds of data with more complex relationships, sometimes about population, education level, etc., and cover the rates, just to throw a concrete example?
Right. So if we have more attributes, as the question explains, are multi-dimensional Gaussian. For example, when it gets to COVID grade or anything continuous, our multi-dimensional Gaussian just grows to include all those dimensions. And the size of our model space, by the way, grows. It's 2 to the power of n, where n is the number of attributes. And if we have more discrete attributes, we'll just add extra categorical models. However, I do want to emphasize here that the competing models idea, even though we did test it on bias and interest in data attributes, it can generalize to other things. For example, if a model represents exploration by somebody who has an internal locus of control versus external, we could build models that observe interactions and infer which type of user we are having with our system.
Okay, thanks. I have one question. So there are a couple of questions from Discord. There is no time to answer to everyone. I have a question about the interaction. You described the hovering and click. Mm-hmm. Did you consider also other possibility of interaction that are different from clicking?
In this work, no. In this work, it was only hovers and clicks. And mainly, we did not collect our own user studies. We used previously collected user studies, and those all had hovers and clicks. However, there is a paper in 2017, for example, on grammar-based interactions and suggestions. I could see, and in that paper, they consider interactions with all buttons and stuff on the screen. I could imagine each task being one model in that framework, and all interactions being captured, and kind of the model selection will translate into which task is being performed, where a task is a model, like a grammar-based model, referring to that paper I just mentioned.
Okay, so thank you. Sorry for not telling other questions, but we are late on time. So please answer to Discord to the question of you. So we move to the next presentation from Jan Zahálka. Is II20, Intelligent and Pragmatic Analytic Categorization of Image Collection.
Hi everyone, my name is Jan Zahálka, and today I'm presenting a paper entitled II20, Intelligent and Pragmatic Analytic Categorization of Image Collections. Images are a very rich data resource. Just looking at this one image, we see that there is a lot going on. There's a cyclist in Amsterdam at a particular location. There's a certain artistic impression from the image, and other semantic information that jumps right at us just from looking at this one image. In the analytic context, however, we more often than not have a collection of images, which is much larger than one. For instance, here we have a data set of 1600 images, and the method of just looking at the thumbnails to gain insight into what's going on in the collection might not suffice for analytic purposes. That's why we need sophisticated tools. Fortunately, multimedia analytics is here to answer precisely this call. Multimedia analytics is a combination of visual analytics and multimedia analysis. The famous visual analytics diagram by Kai et al. Fully applies to multimedia analytics. You have your data, you visualize it to the user, and you load it into the model, which more often than not has an AI component because you need semantic analysis. The user interacts with the model and iteratively builds up insight. II20 is a complete multimedia analytics system for analytic categorization of image collections. The contributions of II20 are threefold. First, it's a completely new machine model. Second, we introduce a new visual metaphor for visualizing image collections, which we call Tetris, after the famous game. And third, we introduce the fast-forward semantic interaction. In analytic categorization, you add images to categories of relevance, which we call the buckets. The buckets are fully defined by you, the user. At any time during your analytic session, you may add, remove, update, redefine, split, and merge buckets to match your current insight and notion of relevance. AI20's state-of-the-art machine model learns to model your buckets on the fly, assisting you in finding images that are relevant to your buckets right now. With its bucket flexibility, analytic categorization is a suitable model task for tasks on the entire exploration search axis. AI20's image view is by default a grid with fairly standard behavior. We can resize it in the control panel, and we can enlarge images by right-clicking on them, which also provides space for any associated information and metadata. Now, let's say we're interested in birds and flowers. So we first redefine the bucket 1 to birds, add the image to the bucket. Then we do the same for the flower, but we have to create a new bucket first. Then we discard a couple of images we don't find relevant at this time. And finally, we hit Show More to obtain relevant suggestions. AI20 provides new suggestions almost instantly. We see pretty good suggestions for both buckets, as well as a small number of random exploration candidates to foster exploration. We can hit Accept Suggestions to automatically label the images, and we can keep going. If you want to review a particular bucket, we can open up the bucket view. Here we can view the images in 2 modes. We can sort the images, and we can also transfer images between buckets. The model updates instantly after each transfer, which implements bucket redefinition, including splitting and merging on the fly. For a change of pace, or when we grow bored of the grid, we may opt to continue in the novel Tetris view. Tetris is a dynamic, one image at a time metaphor, which complements the static batch mode grid. Images descend to the bucket on the bottom and get assigned to the respective bucket when they hit the floor. Tetris is very tightly integrated with the model. You can already see that the model is able to pretty much play the game itself with minimal interaction required. Using hotkeys, we can pause the flow, adjust the descent speed, steer the images between the buckets, and show an image metadata overlay. Let's say we want to really focus on the birds now and rapidly expand that bucket. That's exactly what the fast-forward interaction is for. So let's say that we want 10 more birds right now, so we select birds, specify 10, and we are pretty much instantly taken to the bucket view with 10 new bird images already being fast-forwarded to the buckets. We can review the suggestions. They are marked with the fast-forward icon, and transfer off the mistaken ones. Now we can close the bucket view. To truly support analytic categorization and cover the exploration search axis, the AI20's model has 3 components. The first one is the randomized explorer, which covers the exploration side of the axis. The other 2 are more tailored towards search, the interactive classifier, and nearest neighbor search, which itself is operating in either of 2 modes, approximate nearest neighbors or k-nearest neighbors. The model's pipeline operates as follows, and the components innovated by AI20 are highlighted in blue. Feedback from the user interface is collected. In this case, the user seems to be interested in birds. Then we might want to prune the train images, train the classifier. Then maybe the model asks a couple of Oracle queries, which is verifying the images the model is least sure about. So is this a bird? Is this a bird? And then we move towards producing the suggestions, which is where the magic happens. Instead of receiving suggestions just from the interactive classifier or from the search, the user will receive suggestions from all 3 components in a certain proportion. This proportion is determined by the performance of the interactive classifier and the nearest neighbor search in the previous rounds. In other words, if the user has been receiving relevant search results, then the model will slide more towards search. And when the results become, or the suggestions become less and less relevant, there will be more and more suggestions from the randomized explorer, and the model will be more in an exploration state. Then maybe the user finds something relevant again, we slide back to search, and so forth and so forth. Thus, AI20's model is able to cover the exploration search axis and dynamically slide alongside it, which, to the best of our knowledge, has been missing in the state-of-the-art in multimedia analytics so far. We have conducted two types of experiments. The first was an automated evaluation that used artificial actors, essentially software agents that simulate user behavior interacting with AI20 in a user's place, to answer whether AI20's model is more accurate than the state-of-the-art in interactive learning. The second experiment was a user study on a real use case inspired task, and the associated research question is essentially a sanity check. Is AI20 actually useful in solving a multimedia analytics task? Regarding the automated evaluation, we have observed precision and recall over time on 3 datasets. We have pitted AI20 against state-of-the-art baselines in interactive learning, both in relevance feedback and active learning configurations, and we have simulated Tetris and Grid separately. We can see that AI20 most of the time dominates the baselines on both precision and recall, and we can also see that Tetris does quite well compared to the Grid in many cases, which validates its analytic benefit. So to answer the associated research question, we believe that AI20's approach is certainly valid and improves the state of the art. Regarding the user study, the dataset we used was 8 hours of video, 8% of which was violent online political extremism content, or VOP for short. The dataset comes from a real use case, and it was designed in close collaboration with social scientists that conduct needles in the haystack tasks looking for propaganda among vast amounts of internet content. The task for our user study participants was to establish whether there actually is VOP content, and if so, what kind. None of the participants have seen the dataset before. There are actually 3 categories of VOP propaganda: Islamic terrorism, neo-Nazi, and Scottish ultranationalism. We had 11 users participating, and this is indeed a real task on a real dataset. The observations from the user study were that all users were actually successful in finding VOP content, so they were able to complete the task. To be fair, the response on Tetris was mixed or polarized. Some users strongly liked it, some disliked it, and some saw potential if Tetris would be adapted or if some features would be added. So there might be some future work coming up. The fast-forward interaction was deemed very useful by the users. Finally, a word on time complexity. We have averaged the interaction round times across all datasets. This dataset is roughly 10K images. Celeba is roughly 200K images, and Places 205 is a large 2.5 million images dataset. We are happy to report that all configurations of AI20 run in direct manipulation mode, which is under 2 to 3 seconds per interaction round. And in many cases, this time is slashed further into real-time mode, which is under 0.1 seconds. So AI20 is very suitable even on large-scale datasets. To conclude, AI20 is a complete multimedia analytics system for analytic categorization of image collections. We have introduced the first machine model to cover the entire exploration search axis without explicit feedback from the user. We have introduced a novel dynamic one image at a time metaphor in Tetris and a new semantic interaction in Fast Forward. And AI20 is fully interactive and responsive on even large data. Last but not least, AI20 is available under an open source license, so please feel free to download and use it. Thank you very much.
Thank you, Jan, for this interesting talk. There is one question from the audience. So is about the main difference between in the background work between grid and Tetris modes, besides of course a different interface modality.
So the main difference is how the randomized suggestions for exploration are chosen, because for Tetris you only see one image at a time. So it will just have a small chance of showing random explorer suggestion by default, whereas the grid will always have like a small number at the end every time. But other than that, it's pretty much asking for different numbers of suggestions to the model between Tetris, which always asks for one, and grid asks for more.
Okay, I have one question. It's about multi-bucket. So can you tell something about it?
So the multiple buckets can be useful if you're conducting, say, a forensic analysis. You might want to you might be, or let me go to the user study case. Actually, there are 3 types of extremism. So it might be usefully mapped to 3 buckets. So at first you might suspect well, the suspect from one type of extremism, but then you find that they are involved in more. So you might want to split off a different category, then maybe merge it later, and it's completely flexible, all up to you.
Thanks. Last question is about the success of classification. It is amazing about looking to example of birds. And even small birds were discovered. Does it depend, of course, on the particular data set, or it's more general?
I think it does depend on the data set to an extent. I mean, this was not a birds data set. The demo you have seen was on a general 10K images data set, so not a specialized bird data set. And I think that the lion's share is done by the features that are extracted. So we use very, very good features. Shout out to our colleagues at the University of Amsterdam, who are authors of the DeepNet that extracted the features, and by the interactive classifier and AI20's model proper. But there are easy and there are difficult cases, absolutely. This one of the success cases.
Of course. Okay, thank you. Let's move on the next presentation. The next presenter is Weikai Yang, and it presents a paper titled Interactive Steering of Hierarchical Clustering.
Hello everyone, I'm Weikai Yang from Tsinghua University. Today, I'd like to introduce our work, Interactive Steering of Hierarchical Clustering. This is a joint work with Xiting, Jie, Wen, and Shixiang. Although the hierarchy is very useful to illustrate the relationships among data, users usually struggle with constructing a satisfactory hierarchy from data directly. On the one hand, although there are some data-driven methods to automatically generate the hierarchy, these one-size-fits-all methods often fail to meet the diverse needs of different users. For example, it is not satisfactory that some visualization papers are mixed with machine learning papers because they are about high-dimensional data analysis. On the other hand, utilizing the knowledge from ACM classification system can meet these needs, but it cannot extract some intrinsic structure from the data well. For example, the detailed structure about RNN and GNN cannot be extracted from the knowledge base because it only has a node called deep learning, which is a little bit outdated. Therefore, it is crucial to combine the information from both the data and the knowledge base. It would be more helpful if users can directly steer the clustering through a visual interface to meet their needs. So, there are 3 challenges in building the hierarchy that meets users' needs. The first one is to effectively extract the constraints from the knowledge base. The second one is to utilize the extracted constraints when building the hierarchy. And the last one is to involve users in the building process to generate a better hierarchy. Here comes our system overview. When the target documents are given, we first use the knowledge base to build a constraint tree on a subset of documents, which is knowledge-driven. The constraint tree brings a set of constraints which is applied to guide the clustering process for all documents and generates the clustering tree. So it is a combination of knowledge-driven and data-driven. Users can examine both the constraint tree and the clustering tree and make some modification to them, which are also considered as constraints and affect the clustering, so it is user-driven. Before we go to technical details, I will introduce a case study to show how our system helps generate the hierarchy that meets users' needs. The target documents are papers about interactive machine learning, as well as their reference papers. We first do some node-level refinements on the constraint tree, and we can further adjust them at the document level. The clustering result can also be used to organize the newly published paper. Users can directly refine the hierarchy at the node level. The expert first focuses on the constraint tree. He examines the hierarchy under computing methodologies and finds visual analytics, CV, and NLP. He decides to lift the node NLP and CV to a higher level based on his research interest, and then moves the visual analytics to human-centered computing. Then he focuses on World Wide Web, which has higher uncertainty. The word cloud and titles show that it's mainly about visual analysis research, leveraging the social network for different tasks. So he renames it to social media analysis and moves it to visual analytics. He focused on another highly uncertain branch, discrete mathematics. The branch, combinatories, contains only a few documents, and they are far away from his interest, so he removes it directly. Papers in graph theories are actually about visualization techniques for trees or graphs, so he decides to move it into visualization techniques under visualization. He is satisfied with the constraints and then builds the clustering tree for all documents based on the refined constraint tree. Users can further fine-tune the hierarchy by performing document level refinement. The expert finds a node with high uncertainty, and the content is related to personalization. He shows the constraint distribution on it and finds some blue papers mixed in. These papers are mainly about the natural language processing methods applied in social media analysis. So he moved these documents from the node NLP into the node social media analysis. The refined constraint can also be used as knowledge base to organize the newly published papers. He adds papers from ACL 2017 and 2018. The new papers are highlighted in the visualization. As expected, most ACL papers are classified into NLP, and machine translation is a hot topic. However, he noticed that some new documents entering the node document representations are actually about topic modeling, so he prefers to move it into the node NLP. He also adds documents from NeuroIPS 2017 and 2018. However, the constraints cannot keep up with the quick development of AI-related research. The initial constraint tree failed to provide a detailed structure for deep learning, so he decides to rebuild the local hierarchy with a data-driven clustering method directly. After building the new hierarchy, the word clouds and the titles help him identify several important topics, such as Bayesian learning, reinforcement learning, generative adversarial network, and recurrent neural network. Then he applies the refined constraints and obtains a new clustering result. The new clustering results help him find more related papers. For example, he clicks the documents about GNN in the document list, locates the cluster in the clustering results, and he can find that more papers about GNN are successfully clustered here. After demonstrating the case study, I'd like to introduce the technical details using our system. The first one is to extract constraints. The constraints will show how these documents should be organized according to the knowledge base. A straightforward method is to map each document to the most relevant nodes in the knowledge base, and then a constraint tree is obtained. However, this method does not consider the relationship among data as well, so the nodes in the hierarchy may scatter across the knowledge base. In fact, we can build a better hierarchy if we consider all the documents together. We use ant colony optimization to solve this problem. The idea is that when an ant finds the food, it will lay down the pheromone on its works to attract other ants. Therefore, if the ants lay down more pheromones on a shorter work, then gradually all ants will converge to the shortest work. In our algorithm, each document is regarded as an ant and linked to the knowledge base, and the goal is to find a walk to the root node. However, finding the shortest walk is not our goal. We modify the formula for updating the pheromone tau and introduce 3 desirable properties that a good walk should have. Accuracy A ensures that the path fits the projected documents. The coverage R encourages choosing a node where most of its children are covered by the documents. Structure simplicity S prefers a concise and balanced structure, which is neither too deep nor too wide. By adding these 3 factors, when updating the pheromone, a high-quality constraint tree can be extracted. We conduct some experiments to show the effectiveness of constraint extractions, and the result shows that our methods can extract the constraints with higher accuracy. We also conduct a sensitivity analysis on the parameters of our ant colony optimization, and the result shows that all of them contribute to building a better constraint tree. Then we focus on utilizing the constraints. The constraint tree will be decomposed into a set of fans and triples. A fan means that 3 documents will merge together, while a triple means that 2 documents will merge before the third one. These constraints will be utilized by the evolutionary Bayesian rules tree when generating the clustering tree for all documents. We also conduct experiments on the performance of constraint clustering, and the result shows that the proper constraints can improve the quality of the clustering tree. An easy-to-use visual interface is crucial to involve users in the clustering process. So it is important to generate an informative layout that helps users understand the structure. Since the order of children nodes does not affect the structure of the hierarchy, we can search for the best order to generate an informative tree layout. Here we consider 3 factors in our ordering algorithm. The similarity aims to place nodes with similar contents close to each other to facilitate exploration. The readability aims to reduce visual clutter by minimizing edge crossing. The stability aims to minimize the change between 2 consecutive layouts after user's modification. Besides that, since the users may need to make some modification to the hierarchy, it would be much helpful if we can provide some visual cues to highlight the uncertain structure. The modeling of uncertainty is threefold. The model-related uncertainty indicates the quality of document modeling, and the knowledge-related uncertainty shows how many constraints extracted from the knowledge base are satisfied, and the structure consistency uncertainty reveals how well parent-child relationships are preserved. To conclude our work, we present a visual analytic systems to generate a better hierarchy that meets users' needs. We propose a novel constraint extraction methods based on ant colony optimization, and develop an uncertain-aware visualization to facilitate the iterative steering. In future work, we may further reduce users' efforts by learning from the previous modifications from users, and provide suggestions on the refinement of the hierarchy. The collaborative clustering that involves a group of users is also an interesting topic. Thank you for your attention. I'm happy to take any question.
Okay, thank you, Weikai. So there is a question from the audience. is about the structure of a tree. So you organize the constraint into a tree. Was this simply a design choice related to model interpretability or visual consistency, or does this improve the hierarchical clustering performance?
Well, in fact, the constraint tree is directly extracted from the knowledge base, and then we hope that this can, because it is from the some existing classification systems, for example, the ACM classification systems, and it is more interpretable. And in our algorithm, the constraint tree will be decomposed into a set of the triple and fan constraints, and that will be used in our algorithm to generate the new clustering results.
Okay, thanks. I have a question about the user interface. You have on top of the user interface a constraint weight, which appears a kind of a magic. That slider in which you move the constraint weight. You decide which is the weight for constraints. So the question is, in your experience, the user will understand the number to set, the magic number to set in order to get the results, or it's just a trial and error? You just try a measure and you get the results. If you are not satisfied, you change it.
Yeah, the user can freely change the weights and then to see the clustering results, and if they are satisfied, then they can obtain a good result. And empirically, usually it will be set to the logarithm of the weights will be -5, and our numerical experience also shows that result.
Okay. There is another question about the data set. Would this system work well with data set with less clean taxonomy, for instance, social media?
Our system can also work. And of course, if you can provide some classification systems, for example, if you have organized some of the social media data, and then the system could work well because the constraints will fit the data distributions. And of course, it will fit your personal needs.
Okay, thank you, Weikai. So we move to the next presentation. Is by Pascal Nardini, the making of continuous color maps.
Hello everyone, I'm Weikai from Tsinghua University. Today, I'd like to introduce our work, Integrated Steering.
Hi everyone, my name is Pascal Nardini, I'm with the Leipzig University, and I will present a new web tool to create, edit and analyze continuous color maps using a new color map specification. Let's begin with the motivation chapter. In short, we want to keep it simple. Sometimes it is necessary to modify or adapt predefined color maps to domain-specific semantics. For example, we have here this temperature field and we want to create a specific color map. We have found a cool predefined color map which we want to use as start point, and when we open this color map we see, oh, there are hundreds of colors which we have to modify to reach our color map in mind, and this is a work we don't want to do. But why have some predefined color maps so many support colors? In our opinion, there are two reasons. Number one, the creator wants to determine the path of the color maps through their color spaces, so he can control the process of hue, saturation or lightness. The other reason is that a color map saved in RGB form can keep attributes of other color spaces if it's saved with many close support colors. For example, it can keep the uniformity attribute of the lab color space. Our idea, we propose to separate the specification from the realization of the color map. So we introduced a new color map specification. The main goal of this specification is to use as little support colors as possible to reach the desired process through hue, saturation, lightness, and so on, and also keep a good editability. During the export of this color map specification, we generate many support colors, so visualization tools can use the RGB form of this color map and also use the specific attributes of other color spaces. In the following chapter, I want to tell you more detailed how we have built our color map specification, or in short CMS, to enable a wide range of design opportunities and also get a clear definition for the color map. One part of the CMS is the interpolation, which consists on one hand of a selected color space. At our tool we offer an interpolation at the color spaces RGB, HSV, Lab and D99, and on the other hand the interpolation consists of a selected type. We offer a linear interpolation and a Catmull-Rom spline interpolation. The other element of the CMS are the keys. The key construction consists of two placeholders for colors, the left color CL and the right color CR, and at least our reference value X. Through different combinations of settings for the CL and CR colors, we can distinguish between 5 key types. Let us begin with the nil key. If the CL and CR colors are empty, we get a nil key. Nil keys are always at the beginning of the CMS and initialize a constant band. A second option to begin the CMS is the right key. If the CL is empty and the CR color is set, we get a right key. Like the nil key, right keys are always located at the beginning of the CMS. In contrast to the nil key, the right key initializes a scaled band. The most commonly used key to continue the CMS after the start key is a dual key. If the CL and the CR colors are set and both include the same color, we get the dual key. Dual keys are always located between the start and the end key of the CMS. They initialize a continuous transition point. Another key that is always located between the start and the end key of the CMS is a twin key. Twin keys also have defined colors for CL and CR, but in contrast to the dual key, with different colors. Therefore, the twin key initializes a discontinuous transition point, followed by a scaled band. If we don't want a scaled band but a constant one, we can choose the left key. If the CL color is set and the CR color is undefined, we get a left key. Like the twin keys, the left keys initialize a discontinuous transition point, but followed by a constant band. The end of the CMS is always defined by a left key. With enabling discontinuous transition points, we had a little problem. One goal of our color map specification was to create consistent color maps. This means that all visualization tools should produce the same color mapping using a color map created with our specification. The discontinuous transition point interfered with this goal. Let us explain this with a little example. We have here this simple color map specification with two discontinuous transition points at axis 2 and axis 4. A color map is traditionally stored as an array of interval points with the reference values and the related color. So for our color map specification it would look like this. If now our visualization software would start its loop through this array from left to right, it will find for axis 2 first the blue color and for axis 4 the white color. We created a little test field and would get this color map for the search from left. If now another software also uses this color map but its loop goes from right to left, the resulting color mapping would look like this. For axis 2, the algorithm would first find the white color, and for axis 4, the orange color. We can see that the same color map would create two different results. Also possible is that the color map's creator had a completely different color mapping in mind. Maybe for axis 2 a blue color and for axis 4 an orange color. To give the user this control of the discontinuous transition points, we upgraded our color map specification with the middle of triple idea. This idea of the middle of triple color is very simple. You can see here the 3 key components CL, CR and the reference value X. We extend this definition and add a third color CM. The CM color include either the CL color or the CR color, and so the user can decide what color the visualization software should use if it will find the exact value X. In the tool we realize this with the same key sketch you can see here. Here you can see an example CMS with 2 keys causing the discontinuous transition, the left and the twin key. If a user selects one of these keys, he can choose intuitive the middle of triple color by clicking on the rectangle on the top. For the last part of the specification, we need to talk about the conversion from CMS to the color map with higher number of support colors. Again, I will explain this on a little example. The CMS has all key types except the nil key, and the behavior of the nil key is similar to the left key you can see at axis 3. During the export, the tool creates an array with the key colors. For keys causing a discontinuous transition, the algorithm adds 2 colors to the array, and for the other key types a single color. The left key and similar the nil key have an undefined color for the CL, and they use the CR color from the following key. In the example, this is the blue color at X is 3. Next to this set with the key colors, the tool creates also a set of interval colors. A user can set a number of intervals, and for this example we used a small number of 9 intervals. And then we merge these 2 sets and get a color array with the key informations which control the color map path and a higher number of support colors we use to transfer the color space attributes. We modified this merging process so that the algorithm avoid unnecessary repeating colors from the constant bands, because for constant bands the key colors are sufficient, so the algorithm can skip the calculation of their interval colors. So now we have finally finished the part of the new color map specification, and I can tell you a little bit about the tool. With the CCC tool, we wanted to create a tool that combine color map creation and edit features and also methods for the analysis. We also wanted that every user can use our tool independent from the platform, so we decided to create a web tool, which is available under ccctool.com. And this is all I want to tell you about the tool using the PowerPoint slides. Let us switch to the tool. If you start the tool and skip the welcome page, you can see the My Design sections. Here you can manage sessions with a storage of up to 10 CMS. Sessions can be ex and imported. The tool offers 2 options to start. A user can select a predefined color map from the gallery section, or he can create a completely new color map. Then the tool starts with an empty edit page. On the left side are also the predefined color maps and additional predefined colors for the creation of constant bands. The user has not to know all the details about the keys of the color map specification. He can easily create the CMS with drag and drop of these elements. At this point, I will not tell you more about all the edit methods of the tool. You can visit the color tool tutorial at this conference to get more information. Let me short create a CMS for the following explanations. Below the color map you can see the path plot, which can be used for analyzing and editing. The user can work with different color spaces independent from the selected interpolation space. Constant bands are displayed with a rectangle, and continuous sections of the color map with circles connected with a solid line. For the discontinuous transition points, we use a dashed line. With the path plot, user can analyze and control color components like the lightness. Next to the path plot, the tool has more implemented analysis methods from other scientific work. The user can compare different interpolation spaces, compare local uniformity using different methods, inspect local uniformity with a selected method, like the Euclidean distance in the lab space, or also inspect the global uniformity or local and global intrinsic order. Time is limited, so I cannot show you more about the tool, but finally I want to tell you a little bit about the future work. For the import of color maps from other sources, we need an auto-conversion from the color map to the CMS structure. That means the algorithm has to identify key colors and unnecessary support colors. Next to that, we work on the implementation of color blindness simulation and automated optimization and a testing environment for our CCC tool. And this is the end of my presentation. Many thanks for your attention.
Okay, thank you, Pascal, for this presentation. So let's go to the questions. There are a lot of great features. Can you anticipate your target user? And I would also add your target scenarios. I mean, user and context.
So our first thought is that we want to address users who want to create specific color maps for their application. For example, we have a user from the German Climate Computing Center, and he has to create specified color maps for maybe temperature fields, something like that. So I also created a tutorial with this data set, which you can see at the webpage from the tool. And this was the main goal for our tool. But of course, all other users who want to create a normal color map or want to use one from the gallery section, they also can use the tool.
Okay. There is also another question that is actually very related to those we did right now. Is about how to steer the user into the tool. So there are many tools that propose color maps. So how would be your advertising to get the user to your tool?
So I think I didn't find any other one. We are the only tool which combine the edit and analyze features in one tool. At the moment, we have also a little problem. We didn't have implemented the mapping feature. So if you want to create a color map, you have to switch to ParaView or another visualization software to see your color map on the data. But we implemented a testing section where you can test your color map and see it on different test functions we developed by our own or we found in other fields of the computer science. So yeah, so the main feature is that we combine the analysis and edit features.
Okay. Thank you very much. You answered.
Thank you.
Let's move to the last presentation. Wang is Argus Interactive A Priori Power Analysis.
Hello everyone, I'm Wang from University of Copenhagen in Denmark. I will be presenting Argus, Interactive A Priori Power Analysis. This work was collaborated with Alexander Eisenmeyer, Wendy Mackay, Kasper Hornbeck, and Chet Watanamanokam. Determining sample size is a major challenge when an experiment involves human participants in HCI and visualization research. An underestimated sample size may lead to failure of discovering an effect, even if it exists in the population, which is called type 2 error. It is also wrong to simply increase the number of participants until the results become significant. Moreover, human participants may introduce confounding effects, such as fatigue effect, practice effect. These effects should be considered for designing experiments. A popular approach to determine sample size is a priori power analysis. To calculate the power, we need to estimate the parameters on the left. However, there is an interval relationship between power and the parameters, which can be challenging for researchers to conduct the power analysis. Therefore, we performed analysis to understand what difficulties researchers may have in conducting power analysis. And we summarized these 4 challenges in the paper. For this talk, let's have a look at the second challenge. Researchers estimated multiple values for effect size. This chart shows the relationship between the sample size and the statistical power. One could be a lower bound representing a minimum effect that have practical significance. The effects below the lower bound are too small to be practically meaningful. On the other hand, researchers could be optimistic. Think about the best case. Therefore, the area between these 2 curves are the higher than the conventional 0.8 power could be explored. Let's have a look at the sample size. Researchers could be limited by their resources to a maximum of C samples. This leaves the blue areas for exploration. However, the relationship between power and sample size is not linear. To increase the power by the same amount, more samples are needed. Therefore, weighting the trade-off between power and sample size could be challenging. Existing power analysis tools such as G-Power, Jumper, and Skipper use manual interface. Therefore, exploring multiple power scenarios are cumbersome. Touchstone tool, which is a counterbalancing design tool developed in the field of HCI, allows users to compare power between different counterbalancing designs. However, effect size specification still uses a manual interfaces. Therefore, comparing effect size scenarios is cumbersome. Also, confounding variables such as fatigue effect is not taken into account in their power analysis. Therefore, we propose Argus, an interactive tool to help researchers better plan experiments. Argus takes confounding effects into consideration, supports the exploration of multiple experimental scenarios, facilitates the understanding of the intertwined relation between power and parameters. Let's take a look how we explore power analysis in Argus. Argus is organized into 2 parts. On the left side, users can adjust the controls for the simulation parameters. On the right side, users can inspect the results. Let's have a look at the input controls first. In the expected average view, users specify the estimation of a dependent variable in each condition. With the confound sliders, users specify the effect of the confound and see a preview about its impact on participants' data. In the experiment design view, users can choose how the experiment is counterbalanced, the number of replications, and the number of participants. With the input controls, users can set parameters for statistical result and the power analysis on the right. In the pairwise comparison view, users can inspect how the results could look like. Here, it shows the difference between each pair of conditions as a mean and a confidence interval. The results from the simulation runs are animated to represent uncertainty in a real experiment. The power trade-off view shows the relationship between the number of participants on the horizontal axis and the statistical power on the vertical axis. The history view tracks the change of input parameters. We will show how this works in the following scenario. Let's consider an example scenario of a reading experiment where researchers studied the effect of the reading medium and column layout on the reading time. Suppose we use within-subject design to rule out difference across participants. We are trying to estimate the number of participants we plan to recruit. We started by entering information about the dependent variable. In this study, we use reading time in minutes. Next, we specify the plausible range of the reading time. We then tell Argus how to interpret the direction of reading time. 20 minutes reading time is faster, and 40 minutes reading time is slower. The faster the reading time, the better it is. Then we specify the variability of the dependent variable. This could be a standard deviation from relevant studies in the literature or from pattern study. Let's assume this to be 5 minutes. Suppose we expect the participant who read on screen to take 35 minutes on average, and we expect those who read from paper to take 25 minutes. Also, suppose that we expect the two-column layout to be read faster than the single-column layout. Hence, we adjust bars for the two-column condition by 5 minutes each. Generally, people read at different speeds. Therefore, we specify that across participants they may differ around the standard deviation of 2 minutes. However, reading 4 pieces of text in one experimental session may risk fatigue effect. This increases reading time in later conditions. Suppose we approximate the fatigue effect to be 1 minute. From a trade-off chart, we can see we need around 20 participants to exceed the power threshold of 0.8. Hence, we updated the number of participants accordingly. By inspecting the pairwise variation plot, we can see the reading on paper is indeed faster than reading on screen. For the two layouts, however, it seems there are no significant differences. Suppose we use texts as stimuli that are more mentally demanding than we initially estimated. This increases the reading time in later conditions. Suppose we approximate the new fatigue effect to be 2 minutes instead of 1. With this increased fatigue effect, we see that we need to recruit more participants to reach the power threshold. Hence, we increase the number of participants to 36. By having oval dots in history view, we can compare parameter settings and results which are highlighted in yellow. As we can see, we increase the fatigue effect from 1 to 2 and increase the number of participants from 20 to 36. In comparison, we have a little less power while exceeding the threshold of 0.8. We can also see confidence intervals with the new parameter settings are narrower than with the previous setting. The fatigue effect has a strong influence on the statistical power as we presented a condition in fixed order to participants. This means the last condition is the same condition for each participant. To distribute the condition more evenly, we can use an experiment design that uses Latin square counterbalancing. Now, this design has a higher statistical power. By inspecting the power trade-off chart, we can see 16 participants is now sufficient to exceed the power threshold of 0.8. Hence, we decrease the number of participants accordingly. To evaluate Argus, we recruited 9 participants and conducted a think-aloud study. The goal was to investigate how Argus is used for power analysis and what insights they gain from exploration. There are many interesting insights found from the think-aloud study. I would like to highlight some of them. Overall, the majority of the users reported that they have gained new insights about the experiment design. For example, participants 7 and 8 were not familiar with the carryover effect and the practice effect, but they expressed their understanding of the difference between these effects when they saw the previews. Participants explored the relationship between power and the number of replications and participants. For example, participant 4 said, "The power is very high now. I'm going to tweak replications and participants to see how power is going to change." Reduce the number of participants, power drops down. It makes sense. Participants also interpreted the trend curve in the power trade-off view. For example, participant 5 said, "The power gets stable after a certain number of participants. The current number of participants is a bit too much. We can reduce the number." To conclude, the goal of Argus is to help VIS and HCI researchers consider statistical power when explaining their experiments with human participants. Argus provides 4 key contributions. First, we presented a detailed analysis of a problem domain, then identified the key challenges and tasks. Second, we designed and implemented Argus, an interactive tool for exploring statistical power. Third, we describe a use case of designing a visualization study based on real studies published in TVCG and CHI. Finally, we conducted a think-aloud study to assess how Argus helps researchers gain insights during the exploration. We view Argus as a first step towards an ecology of interactive software tools that improve the rigor of designing and conducting experiments in VIS, HCI, and beyond. Thank you very much for your attention. By the way, I'm a PhD graduate looking for jobs. Please reach me if you found my work interesting. Thanks again.
Okay, thank you, Xiaoyi. So there are no questions from the audience yet, so I have a couple. The first thing is, I am curious to know if you tried to use Argus to experiment, to evaluate Argus.
So we conducted several studies to evaluate Argus, and from the users' feedback, it seems Argus helps people to understand the experiment design and help them to simulate different scenarios in order to come up the final design.
Yeah, but did you use Argus to set the variables? So why did you choose 9 people for the experiment?
Did
you use Argus for the experiment?
Yeah, but actually, we for the experiment we did with the ThinkLab study, it's more qualitative study. It's not quantitative. But the Argus is designed for quantitative study.
Quantitative, yeah.
Yeah.
So that was my second question. So what about the qualitative? So you answered to my second question. There is one question from the audience. Do you consider the learning effect for multiple replicates? So in the simulation, do you consider the learning effect?
Yes, we consider the learning effect. So basically, we call it, in Argus, we call it confounds. So it consists of practice effect and fatigue effect. So basically, also carryover effect. So users are able to explore them via Argus to explore the relationship between confounds and statistical power.
Okay, so this is just a curiosity or a suggestion. So since there are many parameters you can set, there are many parameters. So did you consider as a kind of reverse engineering of the parameters? So you set the results you want to reach, and then you get the intervals of parameters that can be useful to get to that result.
Well, it's not, so basically the design Argus is not designed in that particular purpose. The purpose is more like allow users to explore the relationship and learn from it, and then they could simulate scenarios to get the idea of how those parameters could influence the design.
Okay, thank you very much. So we went to the end of this session. I thank all the people that attended, and have a nice continuation of the conference. Bye bye.
To interactively explore and visually analyze large multivariate data. For example, this cosmological simulation that is clustered into dark matter halos. We create a probabilistic data model in each cluster. We present a complete visual analysis system based on this data representation. which is especially well suited for the density-based visualizations shown here.
We present AgentViz, an application for the visual analysis of call center agent behavior using hierarchical glyphs. Our application relies on a data-driven scatterplot layout, with each glyph representing an individual call center agent. We demonstrate the application with nearly 5 million calls who interact with over 6,500 call center agents. To reduce clutter, we present a dynamic aggregating glyph clustering technique that varies with zoom level, maximizing the screen space.
What do you believe is the correlation between labor union participation and corporate profits of different companies? How would you update your belief after seeing this scatter plot? In this study, we use a new elicitation technique to understand how people update their beliefs about correlations after seeing different visualizations with and without uncertainty depictions.
Many techniques can be used to render and visually explore large 3D line sets with transparency. However, all these techniques differ in several aspects such as runtime performance, memory consumption, and image quality. In this work, we provide an extensive comparison study to discuss the advantages and drawbacks of transparency rendering techniques for large line datasets.
Language models are highly performant across many language understanding tasks. Comprehending the linguistic knowledge encoded by these models, however, remains a challenging problem. We introduced an approach for visually analyzing contextualized embeddings produced by language models. Our design shows how much context is captured by embeddings, the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
It is common for users to struggle to understand how to effectively use TS&E. No idea how to select hyperparameters, assess the quality of the results, investigate the existence of shapes and other patterns. TVS&E covers all these tasks. We provide diverse projections to choose from, global and local quality assessment, investigations of shapes and patterns, and more.
Hey everyone, I'm Junhan Zhao, a PhD candidate at Purdue University, computer graphics major, and a research internship at Bosch Research North America. Here, we are presenting our recent research, Persevere, using factorized prototypes to visually interpret and diagnose deep neural network. This work is co-authored by research scientists at Bosch, Zhen Dai, Dr. Panpan Xu, and Dr. Liu Ren.
We present an efficient approach for volume and isosurface ray tracing of structured AMR data on GPU-equipped workstations, using a combination of two different data structures. Together, these data structures allow a ray tracing-based renderer to quickly determine which segments along the ray need to be integrated and at what frequency, while also providing quick access to all data values required for a smooth sample reconstruction kernel.
Region-based vortex measures are commonly used to extract vortices. The ideal threshold to extract the vortex boundary, however, varies spatially. To detect vortices without manual thresholding, we utilize supervised deep learning. For the regression, we evaluate 3 recent network architectures. The resulting networks are able to detect vortices that grow in size due to diffusion, despite their angular momentum becoming smaller.
We present an interface to visually analyze and steer zero-shot learning models. Our interface is designed to diagnose attribute mispredictions to convey potential failure modes in zero-shot learning. Using our interface, the user can select multiple categories for analysis. We allow the user to steer the model by changing the weights of potentially problematic attributes based on their analysis.
We introduce a direct volume rendering approach that can render encrypted images directly from encrypted datasets. The rendering is performed by operations in the encrypted number space which are dual to operations in the plaintext space. Therefore, the rendering system does not need to decrypt the data. This homomorphic volume rendering approach makes it possible to use untrusted servers for rendering without compromising privacy.
VIS has been successfully helping not only experts but also people who want to learn about AI. At VAS 2018, we presented GANLab, an interactive tool for learning about a deep learning model called GAN. But how does VIS help these learners? We conducted 2 evaluation studies, including log analysis of our demo used by over 100,000 people. We will be sharing our findings with you.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
The transmission of pathogens such as bacteria and viruses is an acute problem in hospitals around the world. Infection control experts need to monitor infections and determine transmission pathways. We developed a novel visual analytics system for the exploration of disease outbreaks. It combines several interactive views and a tracing interaction that allows to detect pathogen transmissions.
Data stakeholders are rarely the data experts. Making tools for them means considering how they communicate about data. Rules are a convenient way for humans to express patterns in data, like we need high variable x and low variable y. In our human-in-the-loop approach, the user selects points of interest and can immediately see rules that differentiate those data from the rest. Lots more detail in the paper, even though it's short.